talking about designing for employability, envisioning tools and opportunities for low-resource job seekers. And that will be at the regular IAS Thursday programming time on Thursday, April 25th at 3:30 p.m., also in this room. So welcome to all of you. If you're interested in signing up for Human in the Data or more IAS listserv information, the sign-up sheet is over against the wall. And now I'm going to turn this over to Professor Lucy Fortson.
Thank you. Yes, thanks. I'm Lucy Fortson. I'm a professor in the School of Physics and Astronomy, and also have a lot of interest in crowdsourcing. Work on projects with the Zooniverse, Galaxy Zoo, and I think we'll hear a little bit about that in Ece's talk. So it's my great pleasure and honor to introduce Ece Kamar. Ece is a senior researcher in the Adaptive Systems and Interaction Group at Microsoft Research. She received her undergraduate degree in Istanbul, Turkey, and she went on to receive her PhD from Harvard in computer science in 2010. She was an intern at Microsoft during her PhD.
Yes, I interned twice.
Yes, right, okay.
Yeah.
And then directly afterwards
Right,
as well. And she was so good that we let her go.
I like the place. I still do.
So she works on developing AI, artificial intelligence systems that combine the complementary strengths of machines and people, something that's very interesting to me as well, and of course something that's very relevant for the theme of our sessions, human data. So she is passionate about investigating the impact of AI on society and studying ways to develop AI systems that are reliable, unbiased, and trustworthy. She served in the first study panel of Stanford's 100-year study of AI, otherwise known as AI 100, amongst many other accolades. And she is currently leading the internal efforts at Microsoft, focusing on improving reliability and safety of AI systems. And so we are honored to have Ece talk. She's going to tell us about the real promise of AI, how to get AI-human collaboration to work.
Thank you, Lucy. And thanks for inviting me to this very special event. I'm very happy to be here and talking with you today. And what I will request is, let's make it interactive. If you have any questions, just raise your hand. If you don't get through all of the material, that's perfectly fine, as long as we have a good conversation for all of us. So what I'm going to talk about today is the space of opportunities and challenges human-AI collaboration introduces. And why this matters? Because in many domains, AI is being introduced to the world that really matter for our society. AI is going to be working with and interacting with people. So how these systems work have real consequences for our society. So that's what I'm going to talk about today. Let's start with the first usual slide that you see in many AI talks today. AI is great. We are making a lot of progress. I think everybody in this room knows about some of these successes that starting from 2016, mainly powered by the advances in deep neural networks and then other neural network-based architectures, we've been seeing a lot of progress in mainly perception tasks like speech recognition, computer vision, object recognition, where on static data sets, machine learning models reaching human-level parity, doing a task as good as humans are doing. And then we've seen all of these advances moving into reinforcement learning style tasks. These include games like AlphaGo from DeepMind, Pac-Man, that's a game that Microsoft mastered recently. We are seeing a lot of successes in well-controlled environments where data is an issue. But what I'm going to talk about today, I'm going to talk about the real world. What happens when we put AI systems into the real world in the hands of real people? What we see is that across many examples, the kind of celebrated successes we see about even perception systems are not as nice as it looks, and there are some rough edges. We are still getting a lot of value from the current algorithms, don't get me wrong, but there are some rough edges we need to be quite careful about. So the picture on the left is a popular, well discussed at least, example from Google. Has anyone seen this before? No? Lucy has seen, and a few people. So Google released their image captioning system, I think 2 or 3 years ago now. And the system is actually pretty impressive if you look at it. So what is this task? You give an image, and the system tells you what is in the image. And you can imagine these kind of technologies being very useful, for example, for people with visual disabilities, right? So, why this is impressive? If you look, can you see the middle top image? There is an airplane there, and from a very limited look at the wing of the airplane, the machine can identify that as an airplane. So that's pretty nice. The problem happened when these 2 African-American teenagers gave their pictures into the software, and the system recognized them as gorillas. So what does this tell us? Errors happen. I think in probabilistic systems, errors are always going to happen, but not all errors are equally important for our society. We would be fine with the system not recognizing the airplane, but once the system is labeling those teenagers as gorillas, that carries a different weight for us. Google is not alone. This is Microsoft's captioning system. And do you remember this dress? People were seeing different colors with it. So this system thinks that it is a cat wearing a tie. Why? I have no idea. So another example, again from Microsoft. Anybody remember Stay? So Microsoft built this Twitter agent that could interact with people on Twitter. And it released it to the internet. People started interacting with it. Initially it was great. There were some functionalities in it that was actually the agent was learning from its interaction with people. There is a big backstory about adversarial action. But what ended up happening is that after the 24 hours the agent was active, it was saying a lot of things that were very offensive. And I love this tweet. This guy tweets that Tay went from humans are super cool to full Nazi in 24 hours, and I'm not at all concerned about the future of AI. Once you dive into the technology and why it behaved the way it behaved, it's actually not that complicated. But we have to be careful about how we are designing these systems. So those are all tasks that are perception-based, these kind of toy examples. But another important trend is that we are seeing AI, mainly machine learning models, entering our world in many applications that are actually quite important for us. Why? Because humans are not perfect. And the successes we see from the AI systems, how good learning from data is getting, is motivating people to actually put some of this technology into critical domains. One example is recidivism. Over the last 10 years, in many states in the United States, machine learning models that predict whether a person in the court is going to recidivate or not is being used to support human judges. And this is not a last year thing. It has been going on for over 10 years. Another example is medical diagnosis. It's a domain that a lot of people are putting a lot of effort into how AI can be useful. We all know about autonomous vehicles and the efforts there. The problem is all of those rough edges we've seen small examples about do exist when AI systems enter to these applications as well. For example, in recidivism, there has been this article from Prof last year that actually documented that the system wasn't behaving the same way if the person was an African American versus a white person. The risk scores that were assigned were different based on the race of the defendant. In medicine, we are seeing after case and case that there are reliability problems. For some cancer patients, the recommendations are not what it's supposed to be. I'm sure you know, Tesla crashes, other kind of concerns. So what is really going on? When we think about AI systems, especially these perception systems, people think about this kind of pipeline. There exists a beautiful data set somewhere that really captures our world perfectly. We divide them into a training portion and a test portion. We use the training data to build a model we like. Sometimes it is very complicated, like a deep neural network with 150 layers. We test it on test data that come from the same distribution. We look at the performance, and we say human level parity, even exceeding it, we are very happy. This is a very simplistic picture of how things are. And here I have a bit more complicated, but it's still pretty simplistic. So first of all, what is my first take on this pipeline? People are everywhere in the development of AI systems. Actually, AI systems are not developed for just recognizing things in pictures, right? AI systems are developed by people, with the data coming from people, and for many applications where people are the end users or the helpers. So, training data comes from people. People take active decisions in the development of these systems. In many cases, they partner up with people. There is a collaboration there, right? And what matters at the end is not the performance of the AI system, it is actually the performance of the team. We don't care about how good the AI diagnosis system is, we care about how good the doctors become when they have the AI system. We care about how good the team of the self-driving car and the human are driving together, how much less accidents we have on the streets as a result of that. So what matters is the team performance. And on top of that, when we test system on static data sets, we really don't see a lot of the complexity of the real world these systems are going to be acting in. So we should actually be evaluating our systems on these real world data. So, what are the some emerging challenges I see from this picture? First of all, we need systems that are trained and developed to be working with people and interacting with people. And one point I'm going to try to make during the talk today is that that is not as simple as just training them on. There's more complexity involved with how a system should be working with a human being. On top of it, we've seen examples that not all mistakes are the same, but the aggregate metrics we use to evaluate AI systems, like 80% accuracy, 95% accuracy, hide a lot of complexity about some of the mistakes that are a lot more concerning than some others. So, aggregate metrics do not tell the whole story about our AI systems. The real world is really massive. There are distributional shifts, outliers. I'm going to be talking about blind spots. So it adds a new layer of complexity into the way we develop and train our systems. And also, in many of these domains we looked at, the decisions have social consequences. If our systems are making different decisions in US courts, that's going to have some consequences about the way our society is structured. And that's why, actually, in computer science, we are seeing new sub-areas forming and getting a lot of attention recently. And those are the main areas I work at as a researcher. So one of them is, how do we augment people and establish collaboration between AI systems and people? How do we do trust? How do we reason about trust? How do we make our machine learning models transparent so that people can understand how these systems are working at? I'm going to be talking a little bit about biases and blind spots, but that's an area that's attracting a lot of attention. And there are a lot of concerns about what is about the ethics of our AI systems. Are there things that our systems should never be used at? Are there things where AI should never be a part of? So I'm going to have a few sentences about that as well. So in this talk, I'm going to try to cover 4 different topics. We'll see how much of that we are going to get done. But the first 2 is going to focus on examples of human AI collaboration and why I personally think it's an important thing to invest on. And in the last 2 parts, I'm going to be talking about an effort we are doing to improve collaboration, and then I'm going to be talking a little bit about reliability. Sounds good? So let's start with the Grosz project. But first, why augmentation? Why a lot of people are interested in AI augmenting people. The fact is, we know there are rough edges, but across these 3 domains, we know that humans are not perfect. We also have our problems. So there is this recent paper from John Kleinberg from Cornell that actually showed that, and we were talking about this yesterday over dinner. They studied human decision-making of real human judges. And they showed that for some of the judges, they were actually harsher before lunch and more relaxed after lunch. Even on Monday decisions, whether their team won or lost over the weekend mattered. So a sign that human decision making is not perfect. We are not perfect. The same thing with doctors. There's a lot of misdiagnosis that is going on and resulting in loss of lives. And we all know that we are not perfect drivers. So these are all examples why an augmentation, if we could improve the human decision making in any of those situations, it would be good for our society. Here's one example I like to motivate this topic. This is joint work from Harvard Medical School and MIT, where researchers looked into metastatic breast cancer diagnosis. They trained models that tried to do this diagnosis. The machine models are not as good as the humans right now. I think the human error rate is around 3.4. The machine had a 6% error rate. In my opinion, the more interesting insight from this work came where they combined the human and the machine together, but not in a real way, but as a simulation. They said, if we knew for any decision who to go to, like would we take the human decision or the machine decision, if they could do that ideal integration, they showed that the human error rate would go down 85%. It will get to 0.5% error rate. So this is just an example to motivate why augmentation matters. And this is exactly what we've seen a number of years ago, where we were looking into the data that's collected from the Galaxy Zoo platform and studied the complementarity of human and machine reasoning. So in this work, I'm sure many of you know about the Galaxy Zoo platform. This is how it looked like when we did this project. The idea is that volunteers can come to this website to look at pictures of celestial objects and classify them into different classes. And the data that's collected from this platform has led to many discoveries and insights in astronomy about our universe. So the challenges, the current practice even today, is that every picture is being shown to many people, 20, 30 people, and their consensus is taken as the result. You can imagine that for many pictures you may not need that many people looking at it. You can actually get to consensus much earlier. And this is something that the machines are very good at detecting. So that's what we did in the Crowston project. And on top of that, we actually used the image characteristics for the machine to build an initial hypothesis. Even before we go to the humans, we could actually infer. For many images, actually, we could infer the correct answer. So that's what the system did. So what it does is that it gets the machine hypotheses and then makes careful decisions about whether to get more volunteer input for the task. And it does decision theoretic reasoning to be able to guide this process to gain the efficiencies. And this project combined machine learned models with a planner to do that decision theoretic reasoning. And what the machine learning models did is that it had features describing the characteristics of the task, characteristics of the work volunteers who were investing their time, because you can imagine some people being so much better at others at classifying certain objects. And it was looking at the evidence that is collected so far. Based on those evidences, it was making two types of inferences. Building a belief about the final consensus answer that would be if we continued collecting more volunteer input, and then making a prediction about what the next volunteer would say if we went ahead and assigned that task to a next volunteer. And these two models were feeding into a Markov decision process. We were using the answer models to build a belief at any time, and use the vote models to build a transition function for the state of the task to improve in the future, so that we could see what is the expected utility if we stop now versus hire one more volunteer. That's what we call the value of information analysis. And if that value of information at the current state for getting one more volunteer input was greater than 0, we were going and assigning the task to the next volunteer. So that's how the decision theoretic engine works. And what we've seen in our experiments is that we could actually gain a lot of efficiency when we put AI in the loop. For example, by only getting 15% of the usual volunteer pool, we could get 93% of the accuracy. And by only getting half of the volunteers, we were getting the maximum accuracy. So we were doubling up how much tasks can be done on the Galaxy Zoo platform without sacrificing anything on the accuracy. So that's just the simple problem-solving task where incorporating AI could actually improve the efficiency. These kind of problem-solving tasks are not the only things where incorporating AI could be beneficial. We just talked about many domains where humans may have biases. Humans may have blind spots, gaps, may have a hard time reasoning about the long-term utility versus short-term utility. That's why a lot of the diets fail. We all want to exercise more and we end up not doing them. So there are a lot of areas where AI can actually be an agent to augment human behavior. Just as an example of that again, we used Galaxy Zoo platform. Why is this moving?
AI is taking
Yeah. Okay, we'll see. I just restarted it, so I thought that may fix it. We'll see. Yay! It's still the simple solution, isn't it? Just restart. So, in this project, what we looked into is how AI algorithms may help people to be more engaged with what they are doing. We did it on the Galaxy Zoo platform, but you can imagine similar ideas might be appropriate if, for example, I have this Apple Watch now and it's kind of bugging me, like, you should be walking, you should be standing. Those kind of behavior interventions, it can be useful for all of us. So that's what we are studying in this project. So what you see here is across the many thousands of volunteers that come to the Galaxy Zoo platform every day, how much work they actually do before leaving the platform for good. What we see is this very common distribution where only a few people do a lot of tasks and many actually do only a few, try it out and leave. Maybe some of them intend to do more, but life gets in the way and they don't end up doing it, right? So what we did in this work is that we did a study of engagement. We said, look, for any volunteer coming to the platform, if we could predict if they are able to disengage from us, right? So in a study setting, you can imagine the system predicting like, oh, this student is going to disengage with me and go watch TV, right? So if we could make that prediction, then the idea would be sending them targeted interventions that could nudge them a little bit to stay a bit more and do a bit more work. So that was the goal. And to do this, we did live controlled experiments on the Galaxy Zoo platform. And intervention is actually a very complex challenge. There are so many dimensions you may be able to design an intervention on. Here we picked only 2 dimensions: time, when do you intervene, and the message, what do you say. In terms of the when part, we got the historical data that is available on the Galaxy Zoo platform because they are logging. When a volunteer comes in, they are logging what they do, what they click on, when they click on, right? All of that data is readily available. So we looked at session histories of users and built a predictive model that said, based on what they are doing so far and their past history, can we predict whether they are going to be here for 5 more minutes or 10 more tasks? So that can be easily done with supervised learning. And we tried 3 different message types. And all of these 3 message types were based on some research that is done on human engagement, and some of this research is done on the Galaxy Zoo platform also, that actually gave clues about why somebody may disengage from the platform. So the first message actually addresses the issue of altruism. Why people come to Galaxy Zoo? Because they want to help. They want to help astronomers. And this message really targeted that dimension. What the message said was, please do not stop yet. You've been extremely helpful so far. your votes are really helping us to understand the deep mysteries of the galaxies. Like just motivation, just say, we really need your help. If you can, please stay a bit more longer. There was some research that actually highlighted the community aspect. The fact that there were so many volunteers and they could talk to each other was a motivating factor for people to come and spend time at the platform. So the second message targeted that. And the third one was interesting, actually. There was some research showing that people were getting anxious. They were saying, look, I'm doing these tasks. They are not trivial. I don't know if I'm doing a very good job. I don't want to be giving bad data to scientists. So the third message was addressing that issue of classification anxiety, saying that don't worry, even if you give one bad answer, we are going to be asking the same question to multiple people and aggregating it. So even if you make a mistake once in a while, it's okay. Right, so those are the three hypotheses. And we did an experimental setup that we hoped wasn't too intrusive. So we were showing these pop-up boxes with the message at most once a session. And we were showing it for only 15 seconds. And people could opt out of the study anytime they wanted by clicking a button. And then we were showing them an intervention messages in the future. And we built this platform, the server that worked on the back end and could run multiple control conditions at the same time. We actually tried 7 conditions in our first studies. There is a baseline of no intervention, of course. And then the remaining 6 conditions are 3x2 combination of the 3 messages and the 2 timing conditions, whether we are timing the message based on the predictions about disengagement, or we are just timing them randomly. We wanted to see how much that predictive model really mattered. Okay. So what you see here is that there was actually only one condition that was statistically significant in increasing the engagement of volunteers on the platform. And that was the one that was getting to the point of altruism. And when that message was timed based on the disengagement prediction. When it was timed randomly, it didn't have a significant effect. And when the model was paired with the altruism message, we could actually see 20% more tasks being done on the platform. Right. And the other thing we've seen, so the blue line that is increasing is that condition, and the x-axis is how much prior history we have about the volunteers, because the more you know about a volunteer, the better you can predict the disengagement and then time the message better. There could also be something about those volunteers being more devoted to the platform anyway. Of course, all of those factors are very hard to separate from each other. But what we've seen is that that particular message actually became more effective the more we knew about these volunteers. One thing though was that, there was prior research that showed that all of those 3 messages helped somehow, or they should, there are some reasons for them, and we only saw effect about 1. We hypothesized that that could be because these techniques about timing weren't really thinking about all of those messages together. It was just a simple heuristic, right? And there is this area in reinforcement learning that is called offline policy evaluation that could actually look at historical data and optimize a sophisticated reinforcement learning policy to be implemented for real without needing to do all of that exploration-exploitation trade-offs. If anyone of you is studying reinforcement learning, you know. So next, we actually tried whether those offline policy evaluation techniques would be more effective in improving engagement. So what we did is that we took the random intervention policy conditions. The 3 conditions were interventions, the 3 different interventions were timed randomly. Randomly divided them per subject onto training, validation, and test sets. And used the training portion to learn a Markov decision process policy, and then use the validation set to use offline policy evaluation techniques to be able to evaluate how good that policy would be. And by searching the space of potential policies, we could actually select a policy that is likely to work in the real world without doing all of that exploration with users. So how does that offline policy evaluation techniques work? We get the past historical data, and we have a target policy pi m that we would like to be able to evaluate. But we don't have data collected for pi m in the real world. What we have is data collected from a behavioral policy pi b. And that behavioral policy in our case is the random policy. And what we do is we actually evaluate each trajectory collected with importance sampling. How likely it is to observe this trajectory if you switch to the target policy from the behavioral policy. That likelihood becomes the weight of that trajectory, and the weighted combination of evaluations become the expected value prediction for the target policy. That's how offline policy evaluation works. On top of that, actually, we observed that this offline policy evaluation technique was quite noisy. It wasn't perfect. So we used the characteristics of our domain, which is interventions could only happen once, to devise a correction process on top of the offline policy evaluation to actually improve the policy estimate. The details are in the paper. I'm kind of waving my hand, just to give you an idea. So why we did this, we actually show that you could learn a much more sophisticated policy than just disengaging based on engagement prediction. So the myopic policy is the one we talked about a few minutes ago. The optimized policy is the one that's optimized based on offline policy evaluation. You can actually see that you gain a lot more by learning a more sophisticated policy. And this policy is actually using all three messages based on the state of the user. And by doing that, it can actually gain a much more improvement in the engagement of volunteers. Yeah. Any questions so far? Yes?
So when you're testing all these different sessions, are you, like, how likely are you to ensure that all the other variables are the same? Like, if it's the same set of tasks, because once something is being classified, a set of images has been classified by a set of users, I mean, you can't make them do the same thing again, right? So how can you ensure that all the other variables are constant?
That's a great point. So we are trying to control as much as possible, but of course there are things that are going to be different between the sessions. And what we hope with that is just collecting more data from each condition is going to add more diversity into it so that some of those effects could actually be leveled off in time. But you reminded me an important thing, which is, yeah, you are increasing the number of tasks people do, but what is the effect of that on their performance? How well they can actually do these tasks, right? Because we are optimizing one factor that may actually negatively influence other things we care about. In this particular study, we measured that and we didn't see that the way people were labeling that distribution was different. Of course, in many other settings, right, you may actually sacrifice accuracy for engagement. So all of those factors should be considered together. We are doing a control study. We are trying to control as much as possible, but of course there are going to be things, you know. And even between the two studies I showed graphs for, the overall trends we could replicate, but the exact numbers we couldn't because the volunteer population had changed between one study to the other. So there is actually a lot of complexity. Yes?
How are you inferring that a volunteer would perform better because of an altruistic message or a community-oriented message? Like, that's what I'm gathering is this optimized policy. But, like, how do you actually
How does that really happen, right? So let me go back to the slide. So this actually approach has 3 steps. There are many ways to represent a volunteer. This approach will only work if we have a good, succinct representation of a volunteer. Then we could look at it and say, oh, this person working this way today would benefit from this message more than that message, right? So it is already assuming that what you know about the volunteer is giving you some information about which message would be more effective for them. Of course, the platform could look at the past intervention histories and see which histories correlate with which type of messages and the effects. But it's actually a complicated analysis. The cool thing is these reinforcement learning approaches could actually detect them in ways that we don't really understand. And I'm going to come, that's actually a problem, right? I'm going to come to it at the end of the talk. But there could be many different representations that could represent the volunteers. And we are actually doing a search over all potential representations with the hope that one of them is going to be more informative for learning that policy that best learns how to incentivize. But at the end of the day, what these rules really look like is a black box. You know, unfortunately, we cannot really open up a Markov decision process easily and understand this logic. And that's one of the, I think, future challenges with respect to transparency and explainability of AI models. Yes?
So just trying to follow here. So
Yeah.
in the optimized model, the optimized policy, you use all three interventions.
They're all potential actions that could be taken at any given
And
stage.
so they were individualized to that volunteer based on what?
History.
And so was it dynamic too then? Did it change based on?
Yes.
Oh, interesting.
So the way the Markov decision process is constructed is that you have a state. That state is a representation of that volunteer's current session and the history. And at any state, you can choose among 4 actions. You could, at this time, you could pick one of the 3 intervention actions, or you could take the action of no op, which is I'm not showing you anything. If you don't show anything, you at the next time step, you have the opportunity to do one of those 4. If you take an intervention action, the future becomes quite clear. I'm just taking a no op because we have that constraint coming from the Galaxy Zoo administrators, right? You can only show it once. That actually gives us some problem structure that we are utilizing in these approaches. So at any time, the Markov decision process is choosing one of those actions that gives the highest expected utility in terms of looking into the future and saying, oops, this action would have the highest expected utility in terms of how much this person would stay. Does that make sense?
Yeah, I'm following you. I'm thinking here. And maybe you'll get to this, but has this model or this method been applied to HR contexts or anywhere outside of this Galaxy Zoo platform?
I'm going to come to that.
Okay.
We are going to discuss Facebook. Wouldn't that be fun? Okay. So those are 2 examples of how AI techniques could be used to augment human behavior, help humans with some of the tasks they do. Now I want to come to the question of, okay, we can do some things, but how do we actually do good collaboration between humans and AI? Is it as simple as applying some machine learning models to some data, or there's more sophistication we need? And I would claim that the reason we are having so much problem with some of those domains is that we are confusing collaboration with automation. Just because we could automate a decision doesn't mean that humans will be able to make use of those decisions, predictions about decisions, and improve their current practices. It's going to require more. My PhD advisor, Barbara Grosz, used to always say that, you know, collaboration cannot be patched on, it needs to be designed from the start, right? And, you know, she would give the example of a convoy versus like just traffic, and how you may have many agents in the same place, but collaboration, design collaboration look different than just people doing things independently. So for this, I'm going to give an example of potential collaboration scenarios, AI-advised human decision making. So we have a very simple workflow. There is an instance coming in, like a patient. The AI model looks at it and makes a prediction, a recommendation. Human sees it, and human makes the final decision based on it. Okay? So, motivating example, we have this project at Microsoft about readmission. We have machine learning models looking at patients who are about to be discharged from hospitals, and making a prediction about the likelihood of that patient bouncing back to the hospital in 30 days or less, and notifying the doctors if they think that probability is high. So that's an example of this AI-assisted human decision-making loop. So why are we doing this? We care about the team performance, right? If we get this workflow right, the final performance should be higher than the AI or the expert alone. That's the whole promise. Otherwise, we would either implement the AI algorithm, remove the human, or not put the AI system in the loop at all. So how does this really happen in reality? The success of this workflow really depends on the humans building trust, building a mental model about when they can trust the AI model and when they should be overriding it. And this is exactly what happens, for example, when people drive autonomous vehicles. Eric Horvitz, my manager, drives a Tesla, and when we discuss his experience with his car, he says that I learned when to trust it and when not to trust it. I learned these streets are safe and these streets are not. People build these kind of mental models. The challenge or the opportunity, both, is that AI models get updated all the time, just like traditional software. So initially you may have a model that is 80% accurate, and the human build a mental model around it. Then the developer may collect more data, may change the objective function, change the model architecture, and ends up having a model, let's say, that is 90% accurate. And now you would expect that when you put that model in the hands of the human, you do an update, the team performance should also improve, right? Not necessarily. So this is actually making two assumptions now, this graph. When I put the machine and the AI together, they should get better. And then when I improve the AI, the team should improve. There are cases that this is not true. And the current way we update AI models today, don't think about this at all. You just update. So actually, many Tuesday evenings, Tesla updates, I hear, the autonomous driving engine. And the next 8 may be working very differently. So the problem is, you build all of this mental model about your expectations, right? Yeah, you should be doing great here, and here I'll take over. And the next morning, that black box gets updated, and all of that mental model goes to trash. So let me give an example. Imagine if you are doctoring this model that is 80% accurate. The red regions are where the model makes a mistake. The green regions where it's doing a great job. After a while of interacting with the model, the human builds a mental model, right? Like, oh, for elderly patients, it's okay. For children, I won't trust it. Now, let's say we update it to a 90% accurate model. But now there's an inconsistency with the mental model. Now it is getting all of the children right, but it's making mistakes for the elderly. So that's what we call an incompatible update. You are incompatible with your previous version. And the way we quantify compatibility is, among the things that the model was doing right when in its first version, how much of it is still doing right? So, it was getting those 8 people right on the first update. It is getting the elderly out, so there's 1 loss. It's getting 7 of the 8 right on that update on the top, so we have 88% compatibility. The one on the right, it is improving. The accuracy is exactly the same as the up one, but now it is compatible. It is getting everything it was getting right before, right? And then adding on top of that. So that's the compatible update. And we built a mechanical Turk task where we could actually study what was the effect of compatibility on human decision making. And to be able to do that, we built this very simple game. It's like an assembly line. We are showing people images, objects of different characteristics, and we are giving them a computer agent that is 80% accurate. That's Marvin. Marvin is giving them a prediction about that box being defective or not. And the way humans can actually do better at that task is by learning when Marvin is doing a good job and when they should be actually investing it themselves, right? We kind of build the characteristics of that AI-assisted human decision task into this very simple game setting. And when we run experiments on this platform, right, we saw that, so they are seeing the same margin until the step 75, and people are slowly learning that mental model. They are getting better in time in deciding when they should be trusting Marvin and when they should be overriding Marvin. At time 75, we give them a new updated model. That model is more accurate. In the yellow condition, that model is this has the same error boundary. In the blue one, it is shrinking, but it is compatible. In the orange one, it is an incompatible update. Right? It's breaking the mental model. And you can actually see that in cases where you have a compatible update, the team performance actually improves with AI improving. In the case where the update is incompatible, boom, the team performance drops. Yes?
So if I'm reading that right though, the compatible error boundary still has less of an improvement than what you would have gotten if you had just not updated it. Right? Because the blue line is below the green.
Yes. Because there's still a change. It's a positive change, but still a change. And a human who is interacting with the AI system doesn't know how to interpret that change.
Is there any research on when it's worth it to update versus not?
I think there's a lot of potential future research that could really look into that. This is one research that shows that just having a better model is not enough reason to update, right? I think the question of when it is appropriate to update would depend a lot on how long you expect the interaction to last. Because there's a future opportunity, right? The human will eventually adopt, and then they are going to get better. And maybe there are additional tools you can use, like notifying the user about the change itself and so forth, that can actually make that a more smooth transition. So it would depend a lot on those aspects.
Sorry, one last question.
Yes.
In your previous slide, you find a way to compute the compatibility for binary tasks, where it's either yes or no. Is there any way to do that for continuous domains?
I think as long as you have a measurement function that could look into how good this action is given the right action is this, you would be able to do that. You need a loss function, basically. That's what I'm trying to say. And loss function is what I'm going to talk about next. So, okay, before that, we actually took many data sets from recidivism to predictive mortality, and we looked into if we updated existing classifiers with more data, what would their compatibility look like? Because if we are getting compatibility naturally every time we update the machine learning model, then we don't really have a problem, right? So what we observed that across these commonly used data sets, just increasing the amount of data you have was actually getting to models that had very low compatibility. So for recidivism, for example, right, the compatibility was 72%. For some other models, the compatibility was like 40%. So compatibility is not something that you get by default. So how do we ensure compatibility? This is what we next looked at. The way we did was just changing the loss function. So you have the regular loss function L. We augmented that loss function with a dissonance term that was selected. So you have your regular loss, and then the new error dissonance, which is our favorite technique. What you do is, if you are working on an instance that the previous version was getting right, add an extra penalty to the loss you're going to have for that instance, because those are the things I want to ensure that I'm getting right. Regular loss functions don't care, right, about which instance is which. We are putting now a bias for the things that you were getting right before, so that you make sure you get them right, so that you don't break the mental model. So that trade-off is managed by that lambda term. And in this graph, we are actually looking at, for different values of lambda, how we can do that trade-off between the accuracy of V2 and compatibility. So, if you want to get full compatibility, you are basically backing off to the original model. So that's this point here. very end. The interesting thing is, for actually a pretty large region, at least the beginning of the blue curve, you are getting compatibility for free as long as you reason about compatibility in your training. Because when we don't put any constraints, you're getting like a 77% accuracy. You can actually push that 77% accuracy all the way to almost like a 65% compatibility, and you don't sacrifice anything on your accuracy. So what we hope that in the future, the developers of machine learning models would be able to look at these kind of graphs and really reason about what is the trade-off they are willing to have on their domain with respect to accuracy and compatibility. It actually becomes part of the development pipeline. Yes?
Would introducing the compatibility term prevent it from reaching an optimal loss function?
Yes, so for the y-axis is how accurate your classifier can be, right? So when I don't really reason about compatibility and I have my original loss, which is just trying to optimize the accuracy of your classifier, that's the low compatibility, high accuracy point, right? Lambda controls how much importance you are giving to compatibility, how much you are willing to trade off accuracy for compatibility. Right? The higher lambda you get, you're basically saying, just give me compatibility, I don't really care so much about accuracy. And that's the point you actually get, like here, right? And for us, the interesting thing is you vary the lambda, you're actually getting points that are doing interesting trade-offs between accuracy and compatibility. And across the many data sets we tried, in many cases you can actually get compatibility for free. Like you have this top region where your accuracy is kind of the same, but you can really change the compatibility in serious ways.
So if you were to set your lambda to a certain value that's big enough, would that prevent the accuracy from ever reaching?
It would. So these very high values of lambda, these, at this point you are basically getting to the accuracy of your original classifier. Because like if you want to get perfect compatibility, you may not be able to do better than your original. But there are all of these data points in between for different values of lambda. We can actually sacrifice some accuracy. In these cases, you are not sacrificing any accuracy at all. But here, you start sacrificing some accuracy to get to a level of compatibility. Okay, so that's, we think is a pretty promising direction. Just thinking about if your goal is working with a human, and you want to be able to make sure that you reason about the mental model that the human has about you, how you should be designing your machine learning models. Because I'm running out of time, I'm going to just kind of mention the last part of the talk because I'm sure you're getting tired. But let me just mention a little bit about the work we are doing for blind spot detection and what we mean by blind spots. So we are seeing case after case that machine learning models are not working equally well for different subgroups of people in our society. The gorilla example is one of them. Since then, we've seen many examples of this. We've seen that speech recognizers have different error rates for elderly, for people with accents like myself, even for women, because a lot of them are trained mainly with male data. This is Jo Boilemani. She's a PhD student at MIT. And when she works on face recognition, she needs to put on this white mask because she's African American and the systems don't recognize her face. So there are all of these issues coming up, and what we're seeing is that machine learning errors are not random. They're actually concentrated. If you have a model that is, let's say, 90% accurate, most of that 10% is concentrated around an input space. It's not like randomly separated from users. The issue is how can we really understand this? And this was a problem we've been working on for the last year or so. For example, Microsoft's face recognition models. We actually saw that the performance of these models were 20% lower if you're a darker skinned woman than a light skinned man. That's a big problem. Right? People are going to be using these services and they are not going to be getting the same performance from them. So why might this really happen? We've actually identified that one of the reasons why these systematic errors happen is due to incompleteness of training data. So the main assumption in supervised learning, and we kind of briefly talk about this, is that the training data perfectly captures the real world concept you're trying to learn. So if you're trying to build a classifier for cats and dogs, your training data knows a lot about all the types of cats and dogs. When that assumption breaks down, so let's imagine that your training data knows about white cats, but doesn't know about white dogs, and you train your model like that, your model is going to be biased against small white dogs. Because you haven't seen them in your training time, but you've seen white cats. You learn that white is a good sign for being a cat. And now, when somebody gives you a white dog, you are going to be making a mistake. And you are going to be making that mistake with high confidence, because you are very sure that that whiteness is a very good feature for being a cat. We are calling those kind of errors unknown unknowns. It's doubly bad because it's an error and you're very confident about it. And we are calling the spaces that capture these kind of errors blind spots, because you have no idea you have those mistakes. So in our work, we've been actually using human and AI collaboration together, human labeling with AI algorithms, to be able to discover these blind spots. Just on a sentence of what we are doing, we are actually putting together clustering algorithms with multi-arm bandits to be able to really discover these spaces efficiently. And this is a line of work that we are really pursuing going forward, because they actually have a lot of, I'm going to pass these really quickly, but they really have a lot of consequences for the way we build our systems. Because for us, once Gender Shades research paper identified that there were these systematic errors for dark-skinned women, there was this big data collection effort that actually fixed these mistakes now. Now these classifiers are working equally well for these subgroups. So if you could identify what are the systematic errors that your classifiers are doing, there are actually effective interventions and data collection strategies you can take to improve them. But if you don't know them, then you have no path for improvement. That's why a big area for us we are investigating is troubleshooting, debugging strategies for machine learning. How do we actually do the rigorous testing that we do for traditional software for the machine learning that we are building? I just want to mention what we are really working on these days. So one is really this issue of augmentation, and how can we build AI that can help people to overcome their failures. Right now we are looking into domains of hiring decision making and seeing what kind of biases we can quantify about people's decision making. And then we are going to be looking into, is intervention is a way to actually improve human decision making with respect to biases. Because I personally think that the main reason we have biased AI systems is because humans are biased too. So there's that deeper problem we need to get there. How do we make collaboration work? I talked about backward compatibility, but transparency is a big part too. That's an area we are doing work on. We have a paper that we recently published on that. We are doing debugging for integrated AI systems. We see the same kind of blind spot problems when agents learn with reinforcement learning. A common technique people use for training RL systems is simulation. For training cars, for training robots. We see that if a simulation environment has incompleteness, let's say that your simulation has never seen an ambulance, the policy you learn from that simulation again has blind spots, concentrated errors around regions where you have ambulances. Again, we are looking into how we can detect that with human input. Ethics. So we did the intervention study, we got good results, we published it, that was pretty nice. Then we stopped and asked ourselves a question. We use all of these sophisticated RL techniques to really change human engagement. What does that really mean? What concerns about ethics, because some of you brought the issue of like, oh, can I apply this in many domains? People have been applying these kind of techniques to decide what you see in social media. People can apply these techniques to make you stay at work longer. Why not? Right? Like, there are many ways these techniques could be useful for some objective, but there are always many stakeholders involved in these decisions. It's not only the people who are building the technology. That's something we have to be very careful about. So this is a question that we're asking ourselves. One other scary thing about this project was that we actually got better results the more sophisticated the approaches got. So we got to these offline policy evaluation approaches. Now we are using complex MDPs. We cannot open them up. You cannot really see how these models are making decisions. So how much accountability do we have on what these models end up doing? So there are many concerns I personally have in terms of applying these kind of techniques, and how actually easy was it to get these results. So this is a big concern in industry as well, and Microsoft has an organization called the Ether Committee. It stands for AI Ethics and Effects in Engineering and Research. And one of the goals is having a discussion around these ethics issues inside the company. I'm involved in these 4 committees, and I think this week Google also announced the committee they are doing on ethics. So I think this is going to become an interesting topic for industry to spend more time over. And overall, I think we have to get really much better at our practices of building AI in industry. Really ask the right questions about training, ask questions about development, and ask the right questions about testing. And we need tools that actually accompany that. So I'll stop there, and if you have any more questions, I'm happy to take them.
What are your thoughts on self-driving cars and human-computer collaboration and communication? Given that the goal in my view should be that the car actually does the driving, and you want to read a book or you get a cab that drives you somewhere. So how do you think is it ever going to be possible to have a self-driving car? Even that you just cannot have this intervention in that scenario.
I didn't ask the $1 billion question, not $1 million, but $1 billion. I think the biggest issue I see is the problem of long tail. And that's one thing that current machine learning techniques are struggling a lot with. So there are a lot of exception cases in the world, and our current techniques are not good at learning that long tail of exceptions. So there was this picture I used to put into some of the talks, like there's this truck, and on the back there is a picture of a bicycle. And when you look at it as a human, because you know the 3D geometry and the physics nature of the world, you can actually identify that as a bicycle picture on the behind of a truck. Not the abilities that current machine learning models have. If you're watching the work that's going on in adversarial machine learning, like Ian Goodfellow's papers and so forth, it is so easy to deceive current machine learning models just by adding noise, putting stickers on all of that. So I think there is a big question about the robustness of the techniques we have, and I think unless there's big advances in the robustness of machine learning, addressing that long tail is going to be a hard engineering problem where you actually do testing and evaluation, and basically try to eliminate those blind spots one after the other. And I think that's going to be the process that we're going to be seeing. Until we get there though, I think human AI integration has a lot of promise if it is done right. In the sense that right now, every time my car is alerting me about something and I actually take an action based on that, the car is learning whether that was a good thing to alert me on or not. The same thing with test errors. They are collecting data about human corrections all the time. What we've shown in our work on blind spots of reinforcement learning is that those corrections are actually very useful to teach machines about what they are not doing well. So until the point of getting that reliability, having human interaction is a good way to collect feedback and improve your AI. However, though, I think the way that interaction works right now is not really reasoning about the cognitive limitations of humans, and I think that's why it's very problematic. Is that?
Yeah.
Yes.
Oh, so question about more of the social
Mhm.
consequences. So I don't know if people still talk about this, but people used to talk about the digital divide, which was the idea that, you know, you had some people who had access to the internet and some people who don't. And I look at this idea of AI and human collaboration, and I think, well, this is just a whole nother level of divide that you know, because we talked about compatibility, and I think about this in the context of a workplace or where you know, big companies are investing. How are we going to implement this kind of technology here so that we can be more productive? What does that look like for people who don't have these skills to work with AI, or what needs to change in our education system in our workplaces to allow people to kind of adapt? Because this is, you know, for better or worse, and you see it, this is where things are going.
A great point. This is actually something we wrote about in the AI 100 report. What does it mean to have fair access to AI technologies? I think, you know, I dream about a future where these AI algorithms are going to be so good that we're all going to become better versions of ourselves, right? That's kind of the hope. But if we don't really have equal access to that technology, that's actually increasing the gap. So is there a question, like, as these technologies get better, is there a question about, is AI access a human right? It should be available to everybody. We don't even have education opportunities available for everybody, right? Is there a question about whether AI availability is going to be access for everybody? So I think that's an important policy question that I think we should be thinking about. But I think that's the reason I care so much about the bias issues too, because let's imagine we can all afford it, but it's not working well for me and it's working well for you. Again, it's creating advantage for you that I'm not having access to. So that's I think why at the shorter term I really care about the bias issues.
Yeah, so I had a question which is, I guess, related to the jurisprudence stuff, but maybe also to the TAE issue as well, which is, it's not so much to do with blind spots, it's to do with the fact that when the input data has a pattern, be it a very strong pattern or even a weak one, that you actually don't want the machine to learn. And so naively, let's take the bias in jurisprudence. So naively, I'm thinking, oh, well, there must be a race feature in the data, I'll just take that out. Okay, so that's obvious, so I presume there is not a race feature in the data. But there is
actually, like, there's research showing that even your zip code.
Yeah, no, I was going to say, so the point is that because of the way that society has been and hopefully is moving away from being structured, there are many things that correlate with race. And as soon as you remove all of those things that correlate, your data become less and less useful, because they also correlate with things that are important to bear in mind. So are there, in your opinion, problems like that where they're almost intractable for AI, and can you see a way where you can get human intervention at some point, maybe like as a human loss or something, you know, somebody checks every result and feeds it back at the end, that you can overcome it and make AI be useful for all tasks?
Yeah.
Long question.
It's a great question. I think in the space of bias and fairness, it is important to separate two problems from each other, because I think the concerns about them are very different. The ones, like, there are objective errors like the speech recognizer not recognizing you, face recognizing not recognizing you. I can collect more data and fix that. That's kind of a blind spot space. That's actually easier. It's more of an engineering problem. You are highlighting concerns about having those problems in our society today, and our models learning patterns from that society and reflecting those patterns back at you. And there is a question about like that, what you're saying is in some cases, that's the truth of the world. Do you want your machine learning model to learn that truth and reflect back, or put some constraint on it so that it doesn't reflect that back? And I think that becomes a value judgment question. What is appropriate? Who decides what is appropriate? Is it okay for your classifier to know about race? There has been actually a bunch of interesting developments in this space in the last year or two, in terms of if you know that there are some things you don't want the machine to discriminate on, there are actually pretty good techniques to enable that. For example, that's actually one area generative adversarial networks have been quite powerful. Because the GANs work, you can actually play that game. You're saying, I don't want to be distinguishing based on this. And if you make your distinguishing model in your GAN to detect race or any kind of sensitive attribute, you can actually train a generative model that actually fights with that and ends up being unbiased on those. So the techniques, in terms of the techniques, a lot of interesting developments. I think the open question is really the value judgment. Like the value judgment I have will be different than the value judgment you have. And how do we actually get consensus on them? And then how do we actually reflect that consensus to the people who are building that technology?
Well, this is sort of related, because it's the question of the presumption that somehow incomplete data implies that there's complete data, but it doesn't acknowledge the potential of bias in the data itself. And so, for example, on recidivism, you might have data that suggests higher rates of recidivism in certain communities because those communities are more actively surveilled or policed, for example. And the second question related to that is then, if I as a human being wanted to evaluate and figure out the trustworthiness of that data and analyze the bias in that data, in most cases these are proprietary and it's a black box. So, which you refer to the black box of the decision making. So how do we think about those issues? Because there's sort of a presumption that you can improve the consistency or the logic of human reasoning with this kind of augmentation, but it doesn't actually acknowledge the flawed nature of the data itself.
Great question. Yes, I haven't really touched those issues at this talk. Coming to the second question first, right? There's actually a lot of work happening on transparency that can actually infer what the black box does without having access to the black box itself. So you can get instances and the model decisions and reverse engineer what the black box was doing. And I think there needs to be processes to be able to have kind of accountability checks on what is being deployed. There is a community in New York, like think tank called AI Now, and they have a proposal out in terms of how to ensure accountability of what AI systems do, and they have a bunch of suggestions. It's not an area I actively work in, but I think that is a very good set of suggestions to actually ensure that those I can't really say that word, but that software that a party sells, how do you actually check what they are really doing? The first question is really about like the data and understanding the nature of data, right? Oh, I think we have to understand that our world is much more complex than our training sets tell us, and we have to be building our models with that sensitivity. I think it is fine to say, I really don't know, I don't feel equipped to build this right now. I need domain expertise to be able to build this and build this, kind of like build a community around building some of the things and not only say, my machine learning model does 95%, isn't that very beautiful?
So on the topic of fairness and access to AI. A lot of the predominant AI models right now take a gigantic amount of data to create and train. Do you think there are any potential avenues to allow people who don't have access to this large amount of data to still be able to harness the power of AI and not give already well-established companies or entities an inherent advantage in the AI field?
Great question. There's actually a report that came out last week. I was involved in one of the working groups about building that US strategy for AI. And the number one issue that came up is the compute infrastructure and data. There are, like, as the results, the current state of art results on some problems, especially on the NLP domain and vision, gets so connected to how big your network is and how much data you have, it actually becomes impossible to do some lines of research if you are outside of that organization. And that's a big problem. That's a big problem in terms of how we are really doing research. So some people are really thinking about what those common infrastructures and data sets may look like. On the other hand, I personally believe that a big advantage of deep neural networks is the representation. So even during our discussions yesterday, Lucy's team was talking about, like, oh, we actually get a pre-trained network and we apply it with the softmax, and now we're just classifying galaxies. So I think we need to be thinking a lot about reusability of networks with different decisions, with different softmaxes, and they may actually ease some of the, that's kind of my personal uninformed opinion, but I think we really need to think about reusability of some of the things we train as well. I'm seeing a bit of that coming through. Yes?
So you talked about kind of needing policies and processes to be able to allow AI and human collaboration to become an actually effective and usable thing. So I'm wondering, because there have been a lot of issues that are discussed in both congressional hearings and also industry and academia regarding these issues, who do you think ultimately has to take the lead, and how has the collaboration between all of these different stakeholders been going in this kind of discussion of these issues?
I'm really not the right person to answer that. So one thing that really has impacted us has been GDPR, the European Union regulation on data. And it was actually very interesting to see the impact of that regulation on practice. Some of it is really about how do you keep the data, what kind of demographic attributes you keep in data, and so forth. But there are actually some clauses in there that actually get into the deployment of machine learning models in the world. So, for example, on domains like loans, for example, they actually have a clause that says that the deployment of the model should enable actionable, steps for the user. I can't really recall what they called it, but they're actually asking for an actionable explanation. And a lot of it actually is still unclear, but what they mean by an actionable explanation is that whenever somebody rejects your loan, they should be able to tell you an actionable path you can take to be able to turn it into a positive outcome in the future. I think it's an interesting step. I think there's still a lot we don't know technically how to get there and whether that's actually feasible. It's a space where right now, especially for those kind of clauses, actually the legal framework is ahead of the research understanding. So that's a bit challenging. But it is definitely one way you can get people's attention on that problem. So there are these interesting dynamics happening right now. I'm not spending my day on it, but even observing them is super interesting. One concern I have is if those decisions are being made without a good understanding of the technical challenges, you may not be able to get some of the positive influences you would like to get. So I think the tech world and the policymakers and whoever else is involved need to really come to the same room, kind of speak the same language, and work together on that. even on GDPR, some of the steps taken to ensure privacy have raised concerns about how you can eliminate some of the bias problems, for example. Because to detect bias, you need to know some of the demographic attributes, and it becomes a chicken and egg problem. And so it's really important to understand what something you do on the policy space influence the technique, and then comes back to you and many other things you care about. Yes.
Recently, Bill Gates mentioned putting taxes on robots due to the economic loss for workers. Do you think that due to how software and machine learning will automate away different other types of jobs, that we should look at economic solutions, specifically on AI systems?
Again, it's not my area, but one thing I would say is that, my personal opinion again, I think working and having a job is more than making money. I think we see that even when we study crowdsourcing. When people do piece-by-piece work. People take ownership of what they do. It becomes part of their identity. People have all of those altruistic messages that will be discussed today. People take ownership of what they do even if they are not making money out of it. So I think the issue of people losing jobs is not only an issue of economics, and we have to think the personal and the social part of it as well. So whatever solution we find needs to be enriching and empowering people. And I think money is really an important part, right? We all need money, but it's not the only thing that we care about in that conversation. I would really hope that as we really discover that augmentation, maybe we really realize that, humans are useful for some things too. I don't think that our goal is not producing more humans. We have a lot of humans. I really think we need to figure out how to use humans better instead of just getting tasks out of them. So maybe we should start also more looking into those aspects as well.
And if I can ask a follow-up?
Yes.
So people are talking, like you said right now, policy is advancing far ahead of technology.
Sometimes.
Some
That's an example. Yes.
Do you think that this needs to happen, that policy needs to get ahead of the technology and implement changes now and try and, should policy try and fix the problems that they foresee now instead of waiting for the problems to show up later?
I don't know.
How do you predict what's going to show up?
I don't know. I think everybody should probably put a stake on the ground and say, I care, let's come and talk. I don't know which should go first. It's not something I'm an expert on, but it is really problematic if people are not talking.
So I guess that's your plug for Aether then?
Not necessarily, but I think here's the thing. Looking from I'm somewhere between academia and industry, right? I see both worlds with my limited capacity. The conversation has been evolving very interestingly. It's actually a very fun time to be on this field, in the sense that 2 years ago everybody was like, deep neural networks, AI is going to do everything, and then even when you go to NeurIPS and look at the proceedings, you see that it's not only about neural networks and how well it is, and people are raising all of those issues now. There is a process of maturity that's happening in terms of understanding the capabilities. Now a lot of people are concerned about many of the things we talked about today. That's a first step. People are thinking. Now everybody is trying to organize whatever they can organize to actually improve some of the practices. Ether is Microsoft's way. It's an experiment. We'll see. There is also partnership on AI, which is across companies and NGOs trying to address some of those questions. Again, it's an experiment. I'm sure there are many committees happening in many places in the world, right? So, things are bubbling up. What is the ideal structure that's going to get things to work? I don't know. We'll see. That's the next